Good morning from me. Good afternoon to most others that are on this call. My name is Joe Nuth, and basically I'm going to talk about something that is very simple, actually, and should be reasonably obvious once we're done. All right. The question is, did a complex carbon cycle operate in the inner solar system? And the reason I'm going to tell you this, and what I'm going to tell you, is that if you look in the interstellar medium and you ask questions about what the distribution of solid grains are, you find that most models are very, very mixed. Carbon grains, carbon coatings on silicate grains, they're basically all together. And so there's a consequence to this when the materials get hot. Basically, the carbon reacts with the silicates, makes carbon monoxide, and the carbon grains generally get destroyed. They have to be reformed. And so I'm going to talk about some of the reactions that we've done in our laboratory that looks at what happens when carbon monoxide and hydrogen get together on grain surfaces. It's not very hard to visualize what happens. What is surprising is the kinds of results that we get and the reaction products. The answer to the question, in case you guys have to leave early, is yes, there is a carbon cycle. Basically, you destroy carbon, you make carbon monoxide, and you reform a different type of carbon in the inner solar system. So that, in a nutshell, is pretty much the presentation. All right, in the interstellar medium, most carbon is in the form of solids, at least according to most models of the interstellar extinction. Most of the metals, the carbon silicate grains are extremely well mixed, and the grain size distribution, if you believe Mathis, Rumpel, Nordsick, and some other modelers, is basically a fairly steep curve at the radius of the grains to the -3.5 power, roughly speaking. It goes from -3 to -4. Graphite grains basically are very tiny, 0.005 to 1 microns, while silicate grains are, again, very tiny, up to a 1/4 micron or so. The problem is that if you get grains much bigger than these, you run out of carbon or silicate before you actually can finish the extinction curve. You just don't have enough mass to go to very large grains and still make the extinction curve as observed. So you basically have small grains, and that's the trick. Matrix is very small, down to micron range. Lots of other components are in the lots of other components are in the millimeter to centimeter range. You've got CAIs and chondrules that are all fairly large. Carbon is much less than 10% in chondritic matrix. And the bottom line on that is that most silicate dust has been thermally processed to a fairly large degree. So these two are intimately mixed. And the silicates, we know, have been processed to fairly high temperatures, so at least to the melting point. So if you've got grains in the interstellar medium that are mixed together, whether they're fractals, whether they're grain coatings, whether they're silicates inside some matrix of carbonaceous material, or even just gathered together closely, these things are very, it's a very well mixed mixture. The thing that happens when you, let's move. There we go. All right. The thing that happens when you take those to high temperatures is you basically do exactly what we do when we're smelting metals. The carbon reacts with the silicate, you make CO or CO2, and you get metals left over in that particular case. So most pre-solar grains, silicate grains, have been heated to at least the melting point or higher, not quite vaporization. Some of them have been heated high enough to vaporize and recondense these things. Some of them have been heated high enough to make CAIs, which basically distills most of the most of the metals out of the grains themselves. So that means that the pre-solar carbonaceous solids that we had, the things that were made in circumstellar outflows, the things that were made in the cold cloud before the collapse, have all been converted to CO or CO2 by reacting with those hot silicates, and therefore they're severely depleted. But that also should mean that the gas is enriched in carbon monoxide, carbon dioxide, and hydrogen. And so in the inner solar system, you've got the perfect setup to do catalytic conversion of that back into organic materials. The simple Fischer-Tropsch reaction, we stopped using that term because people got upset. They were thinking Fischer-Tropsch is one very specific process, and it is. Carbon monoxide plus hydrogen goes to various hydrocarbons, usually the simple hydrocarbons, methane, ethane, etc. And in this particular case, that's not what happens. They certainly react to form various hydrocarbons, but they form much messier systems. And the catalyst is not left alone and back at the starting point, which is the main sticking point for not calling these catalytic reactions, but rather surface mediated reactions. We've done experiments in a very simple system and using a very simple gas mixture. So this is fairly straightforward. What happens in this system is that we put analog silicate materials, silicate grains, dust that we make in our laboratory, that resembles fresh condensed silicate smokes. And in here, we basically circulate a mixture of carbon monoxide, nitrogen, and hydrogen, plus a little bit of noble gases, inside a heating mantle. The tube comes down the center, and we basically get a reaction with the silicate grains here, and the materials continuously flow out. They go to a spectrometer where we continuously monitor the spectral evolution of the gas. We have a pump here, which is a bellows pump, so that we don't have any organic contaminants in this system. This is a ballast, basically, because the pump pumps in jerks, and so we don't want that. We want a much cleaner and smoother distribution of the gas coming through here, so it's just a flow. And again, so we continuously monitor this reaction. It's a completely closed system in this case. What we start with is basically pure carbon monoxide. This is a half an hour after we've started at a temperature which actually I don't see on here, but it's typically on the order of 350 to 450 degrees C. It can go up to 600 degrees C. And you can see that we start to make the carbon dioxide, water. It progresses. This is after 1.5 hours. Again, you're starting to get methane now and a nitrogen compound here, CN-ish reaction, CO2 as well. These continue to grow. Carbon monoxide continues to go down. And so we're making more and more complex hydrocarbons here, 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 and here. The spectral changes are pretty obvious, and it's obvious that the CO is the feedstock to make the rest of these compounds. We get a variety of compounds, a whole variety of compounds in the gas phase, and after we do GCMS analysis, the simple compounds, carbon dioxide, methane, and water, even more complex alkanes. We get aromatics. We make ammonia, and that ammonia also reacts with the materials that we're making. We get the aromatics, ethylbenzene, benzoic acid, methylamine, so the precursors for amino acids, and even more complex hydrocarbons. It gets more complex than that in a sense later, but the gas phase composition is continuously changing. Carbon monoxide is going down, CO is going up, but there are intermediate reactions that go on to give us various hydrocarbons that then decay over time. What was unusual about the experiments that we ran is that we assumed that the Fischer-Tropsch catalyst would be poisoned by the materials that stuck on the surface. What we found was exactly the opposite. The materials that we were using, the analog iron silicates and magnesium silicates that we were running, actually got better as we ran one after the other. The way we did these experiments was to put the gas mixture into the bulbs. Then we ran the experiment at temperature until about 75 to 85% of the carbon monoxide was depleted. Then we took the gas out, we refilled it with a new mixture and ran again. And as we ran more and more experiments, 10 to 20 experiments on that same catalyst, it turned out that the reactions got faster and faster. As we started, we had a slow decrease of the carbon monoxide, relatively speaking. As we increased the number of runs, we got faster and faster. Same with getting the products, the methane. The first time we didn't get quite as much methane, and it went up slower. As we used that catalyst over and over, we were getting more and more methane faster as we ran. This is 600 degrees C. So what was happening was the catalyst was getting better and better. That shouldn't happen in a normal catalytic reaction. And in fact, it was fairly unexpected. So what we demonstrated in these reactions is that surface mediated reactions occur on lots of surfaces. We did iron silicates, magnesium silicates. We actually even did graphite at one point. Every time that we ran, we would start out very slowly. The carbon monoxide or the methane, the carbon monoxide depletion or the methane increase would be relatively slow. But as we use that catalyst, something that we were depositing on the surface would actually enhance the catalytic activity. And so the coating actually was a better catalyst than virtually any of the materials that we tested as our starting catalyst. And the complex organic material was obviously not only going into the gas phase, but depositing on the surface. And that surface material was a very good catalyst to convert carbon monoxide into hydrocarbons. It was a macromolecular organic coating. And so, well, the way this is set up, I can't even read my own slides. When we set this up, the question then is, how do we prove that this is happening? What do we say is going to be in the grains that are coming back from, say, Hayabusa or the OSIRIS-REx mission? And so Hayabusa's already brought the samples back, and OSIRIS-REx will be bringing samples back in September. So what do we predict will be in those materials? Okay. We looked, the macromolecular carbon deposition is temperature dependent, but it isn't very much. So what we were looking for is possibly an isotopic signature to see whether or not these are going to be enriched in carbon-13, depleted in carbon-13, whatever. We did the experiments with carbon monoxide that was normal right out of the bottle, basically at lower and successively higher temperatures, and we did get a change in the carbon monoxide, in the carbon isotopic composition. It got lighter as a function of temperature, but not by enough to really tell, especially if these materials circulate in the solar nebula from slightly higher to slightly lower temperatures. All these temperatures are possible within pretty much the same region. And it's unlikely that one set of materials will stay in one region exclusively. So it's really going to be hard to tell from this, from the isotopes of carbon, what temperature, what conditions these things were made at. It just isn't a very large spread in isotopic composition compared to the temperature. So, okay, doesn't want to change. My slides, oh, there we go. Now it's jumping all over. All right, one other thing that we can report is that Friesenstiel in 2009 reported graphite whiskers forming in several different types of carbonaceous chondrites. The initial discovery here, you can see this is a lab-grown graphite whisker, and here is one of the whiskers they find basically growing on a CAI in Allende. So one of the possibilities is to look for carbonaceous deposits on these materials. And so we did some experiments. Again, this is graphite starting material. This is an iron silicate starting material. We managed to circulate the mixture at modest temperatures, 873 K, 600 degrees C, over these, and you see the formation of carbonaceous nanotubes. These are cup stack nanotubes when you take them out. Even on the graphite, the nanotubes grow, and obviously this is a continuous reaction along what would be the C-axis of the carbon. Again, same kind of thing happening on the surface of the iron silicate materials. We wanted to do some more quantitative reactions on the rate of reaction. So we did this on iron. This is an iron wire, 0.009 inches in diameter. This is the product after, it's at the same resolution. This is the product after we run at modest temperatures, 600 degrees. Yeah, 600 degrees. For a time in our experiments. And you can see that these nanotubes grow out, they get fluffy. We hypothesize that this is one possible way that if these grow on surfaces of hard silicate materials, they enhance the sticking coefficient. So it's one of the ways that you could potentially grow larger bodies that just don't bounce, the grains don't bounce off one another. They actually start to accrete fluffier outer materials. We measured the CO decay rate, so we measured the rate of the reaction as a function of temperature and time. And so we used, this is on that 60 inches of iron wire in the experiments at various temperatures. The activation energy for the reaction was 127.8 kilojoules per mole. So this is just for the simple reaction, Fischer-Tropsch reaction. The activation energy is anywhere from 96 to 105 kilojoules per mole. So we're basically in the ballpark in terms of our measurement. Now, chondrules and CAIs form in the 1,000, 1,200, 1,500 K regime. And so we can extrapolate that rate, and we built a separate system, there you go, to predict what the reaction rate would be, how fast these reactions would form those little carbon whiskers that we were seeing, that Friesenstiel were seeing in the CAI. And so we should be forming millimeter scale whiskers in about 5 hours if we extrapolate this. Nebular pressures are from 10 to the minus 3 to 10 to the minus 4 bar, and CO is 10 to the minus 4th of that total. We're not going to operate at this low a pressure. In fact, it's kind of hard to actually meter materials in at that low pressure. So we assumed that what we're doing is effectively moderated or controlled by the reaction rate, and the reaction rate is controlled by the number of collisions of carbon monoxide or hydrogen with the surface of the grains. So we assume an average gas temperature of about 1500 K, and at a high temperature for the formation of the chondrules, things happen in about an hour. So we extrapolate that relative formation rate of whiskers at these temperatures. And unfortunately, well, let's start first. We built a new reaction system in order to make those measurements. The green points were taken basically with the glass reaction system I showed you before. The red points were taken in this new system. So the two systems agree with one another, roughly speaking. At the lower temperatures, the red points are fine. When we went up in temperature, obviously the reaction rate went down at this point. So we peaked out somewhere around 1000 degrees Kelvin, and things went back down. So that's the danger of extrapolation, obviously. Surface mediated reactions don't work at temperatures around 12 to 1500 Kelvin. It's not that surprising, obviously, but there we go. What we do know, a couple of things, obviously, is our pressures are too high and our temperatures are too high and our pressures are too high. The experiments basically that we do are at near atmospheric pressure. The grains in the Solar Nebula have about 100 to 1,000, 10,000, maybe a million years at much lower pressures. Didn't know I did that. Our experiments last for months. If we tried to propose to do experiments that last for 100 years, I doubt we would get funding. CO grain collisions are what control the reaction rate. So the pressure is a proxy for reaction time in this case. So experiments that we do at 1 atmosphere for approximately 1 week are the equivalent of what happens in 200 to 20,000 years in the primitive Solar Nebula down at pressures as low as 10 to the minus 4 to 10 to the minus 6 atmospheres. In terms of the temperatures and the reaction time and how long it takes, we do experiments at 400 degrees C or 873 K. The reaction lasts basically for about 3 or 4 days. The experiments, if we do the 20 experiments that we do in order to get the products that we see, for 20 runs, it takes us 2.5 months to do those. At successively lower temperatures here, so the 600 degree, 500, 400, 300, 200, if we were to do things basically at 373 K, it would take us 111 months, which is pretty much going on 10 years. Again, it's much too long to do these experiments. So we have to extrapolate to some degree. We're stuck. On the other hand, going to high temperatures, there were experiments that were done by Chaitanya Giri, Andrew Steele, and others at Carnegie. And they did form at high temperatures, about 1300 Kelvin, on an aluminum oxide material, basically a carbonaceous whisker. It's basically here. The whisker contains other materials as well. The point is that at high temperatures in a plasma, you can get carbonaceous deposits of solids. So you can make carbon solids from these materials at high temperatures, but it has to have a plasma. So the let's see, the roundup here, this is hard because I can't see my own slides. Most silicate grains in meteorite matrices were completely processed at least to the melting point. Many were processed beyond that, and some were effectively distilled so that the silicates and more volatile metals left them to make CAIs. The intermediate processing basically gave you chondrules. Others were hot enough that they melted and the surfaces basically drew them together into solid grains. The size distribution of the initial materials was small. The size distribution of the matrix grains after processing was much larger. So that meant that the silicate grains, which were intimately mixed with the carbonaceous grains, were processed to high temperatures. Those carbon monoxide grains processed to high temperatures in the midst of silicates. Basically, they reduced the silicates and were oxidized to carbon monoxide, possibly CO2, at these reasonable temperatures. If you put carbon monoxide together with the hydrogen and nitrogen, you can form an entire range of new carbonaceous materials, and you can, at very high temperatures, form them into nanotubes and graphene whiskers in plasma-rich environments. So you convert the initial carbonaceous material to CO, and then you convert it back into new carbonaceous solids that are different than the ones that you started with. Of course, these materials are all circulating in the solar nebula. So the processes that happen in the inner nebula make materials that are transported out to the comets and the materials that are also falling into the inner solar system. So that now you should have two different types of carbonaceous materials in your small bodies that collect these materials. And I'll get back to that in a second. Pre-solar carbonaceous grains and coatings do survive in the outer solar system, but as they fall inward, they're progressively destroyed. Plasma processes and just thermal processes, lightning, electrical discharges, melt the silicates and bring these intimate mixtures to high temperatures, and those convert the carbonaceous material that was originally there to carbon monoxide, and the metals basically stay. The surface mediated reactions operate at lower temperatures in the inner solar nebula to convert that carbon monoxide back into different types of carbonaceous material. Very large nebular circulations basically bring these materials from the inner nebula out to the outer solar system, and thermal and hydrothermal reactions in planetesimals that these solids basically go into can convert carbonaceous solids into many other potential products. So for small bodies in the what we're looking at is the type of carbon diagnostic of where they formed in the solar nebula. Carbon in the outer solar system should contain the full range of pre-solar and solar materials. Namely, we should find circumstellar condensates from carbon-rich stars. We should find products of low temperature molecular cloud reactions, those that form the obvious enrichments of nitrogen-15 and deuterium, etc. Products of surface mediated reactions should also be there because they get transported outward due to nebula circulation. That's the same reason that you find in stardust grains crystalline silicates. They were annealed and formed in the inner solar system, and they were transported outward by these same outward flows. Carbon in the inner solar system, on the other hand, is going to contain very little of the carbon-rich material formed in carbon stars or the low temperature form material in the molecular clouds, because that material is going to have been destroyed and should be dominated by the surface mediated reaction products that are synthesized in the inner solar system. So the planetesimals, the meteorites that come there ought to be diagnostically, well, you should be able to diagnose where they formed because of their carbon chemical composition. And basically, that's all that I've got to say. Thank you very much.
Hi, Joe. I wondered if you could say a bit more about why the catalysts get better the longer they run for. What is really changing on the surface that's making them ever more active. And it looked from your experimental data as that sort of plateaued after a while. So they started off very relatively poorly performing, and then after the increase, it sort of leveled off again.
Yep, you're right. What basically happens is we form more surface. In other words, when we started off with a nice clean iron wire, what we have is a particular surface area. And so the carbonaceous material grows on that surface area, and this carbonaceous material is actually a better catalyst for these type of reactions than iron is. In fact, we measured the surface area for, in other experiments that I took out of this talk, for magnetite grains, and we almost got 7 times more surface area by the end of the reactions after we did 20 reactions. The surface area of the material kept increasing. We measured the surface area using the nitrogen technique. So it's not that the catalyst itself gets better, it's that the catalyst produces more surface area eventually. And this works on almost anything. Magnesium silicates, when we first tested them, had virtually no reaction. Nothing really happened. Turns out that when we went back and more carefully looked at the data, a trivial amount of reaction happened. And after 5 or 10 experiments, the magnesium silicate initial starting material was getting as good as the iron silicate material. And then it kept getting better. And it's not that the magnesium silicate was the great catalyst. It was the magnesium silicate slowly formed these materials, this carbonaceous material, and the carbonaceous material grew on the surface. And as that grew from the few spots that initially were there, basically the reaction eventually took off. So it took us a while to understand that the catalyst, that surface, was only good for the initial parts. And then it was, from a Fischer-Tropsch point of view, this would be completely poisoned because it would be completely covered by the carbon material that we were depositing. The mag silicate was covered much more slowly. But once it was, then the catalytic activity that took place on the coating, the carbonaceous material, was much more efficient than what took place on the surface, and the rate took off.
Thank you. Very interesting work. Thanks.
Well, like I said, the problem basically is you don't want to talk about this as as Fischer-Tropsch reactions, because the normal chemist will say this isn't Fischer-Tropsch. And it's pretty obvious because the active surface is changing over time. And as this carbonaceous material is deposited, the rate of reaction goes up, not only because the material itself is a better catalyst, but because the surface area increases.
Yeah. Thank you.
And for any radio astronomers on there, I would also like to say I'd love to see ALMA data on protostars, because in the very innermost regions, you should have an increase in CO. But I don't know that anybody has seen that. All right, let's see. You had a hand up, Jay Ali?
Yes.
Yeah.
So I had a question that, so from the experiments where CO reacts with hydrogen to form like hydrocarbons, for example, so even if considering so like astronomical objects like disks, so protoplanetary disks, so even if the gas is enriched in O, we can still have carbon dominated chemistry on the grains in the disks. So that, like, is that what?
Yes, you can see that we were making water, for instance, in those reactions as well. There's plenty of oxygen in that system, but the carbonaceous materials still deposit. They have oxygen in them. I mean, we had the products that have oxygen in, like for instance, the acids that we made, we also have nitrogen in that system, which reacts much more slowly than the carbon monoxide does, but still gives us CN and amines in the reaction products. So the products are much messier in our simple system, even though it's not as messy as nature, but nowhere near as simple and clean as the chemistry that normally goes on in chemical plants that use a Fischer-Tropsch reaction, for instance, or some other catalyst to convert specific feedstocks into specific products. So again, that's not a surprise. They were optimized to make those products as cheaply and as efficiently as possible. So
Yeah.
But yes, you make the carbon which has oxygen in it. You have the carbon that has nitrogen built into it, and I wouldn't be surprised. Well, and we also, by the way, in this material, we can trap noble gases. So again, we can have a lot of different materials in the carbonaceous product here, but they're not the same as the carbonaceous products that started out there. In other words, the low temperature chemistry that happens in the clouds that puts N15 and deuterium in the carbonaceous material for the outer solar system is not surviving here. These things are isotopically normal.
Yeah. Okay. Yeah. Thank you. Thank you.
Mhm. By really murdering names. Aditya?
Yes, yeah, thank you for the very interesting talk. I was wondering again about the hydrocarbons. So from what I understand, kindly correct me, what I see is that you first form hydrocarbons due to something similar to a Fischer-Tropsch, but then that continues to grow into a more complex and messier hydrocarbon chain to form these carbonaceous materials. And these things prefer to happen in higher temperatures, which is in a protoplanetary disk. Again, it is in the very inner regions closer to the star.
Mm-hmm.
So my question is, if that is the case, then if we look at these hydrocarbons as, say, ices or something like something that is adsorbed onto the surface, then what we would expect is that at the high temperatures in the inner disk, they would basically dissolve from the surface and go into the gas phase of the disk. And that should be basically be observable through, say, near infrared or mid infrared in these protoplanetary disks. But as far as what we have seen through Spitzer, we see only CO, CO2, and C2H2 carrying the carbon. So do you say if we see these hydrocarbons in the inner disk, then this is probably the scenario that's happening there?
In the innermost disk, the thing that you will see most easily is carbon monoxide rather. That should come from the high temperature processing of the initial carbonaceous grains that are intimately connected with the silicate. May only be in the innermost material, in the innermost regions of the nebula. You can see the kinds of stuff that we make are relatively benign in a sense. I mean, you should see some methane generation and definitely see water. On the other hand, water is already there, and you'll see some carbon monoxide. Again, these are at much lower levels than the carbon monoxide that comes out. The problem is that these don't all just come off the disk. When we did some experiments to find out what the branching ratio was from the volatiles to the solids, that depended on the initial catalyst, but it eventually settled into around 30%. So about 30% of the carbon actually went into the solid carbonaceous material that we saw, that macromolecular material, and about 50 or so percent went into a whole range of hydrocarbon materials, hydrocarbon in the generalist sense that obviously things like ethylbenzene and acetone, benzoic acid are much more complex. So I'm not sure that you have the sensitivity to see much beyond the simple things like methane and ethane. You won't necessarily see these things because they're down by probably 6 or 7 orders of magnitude from the methane in that case. You'll probably also not be able to see the carbonaceous solids that, because again, they have no real spectral signature that's different than carbon on the surfaces of grains. So
Yeah, okay.
so
So
the
you-
only thing that you might see is an increase in carbon monoxide. But that probably only by a factor of 3 or 4. Maybe if all of it was converted, you would see a factor of 6, but all of it's not going to be converted at once.
Okay, so basically the carbon that is producing the CO is basically from the grains themselves. So pre-solar formation, like before the protoplanet disk actually forms in the clouds, the grains themselves has this carbon in it. So
Yes.
then the solar carbon to oxygen ratio that we generally assume as 0.45 or something like that, is that accurate? Like, does that match with what you propose here?
Yes. Yeah, I mean, we're taking normal cosmic abundances, and then on top of that, you're using the models of the interstellar grain population that matches the interstellar extinction curve. Whether or not it's the Mathis-Rumpel-Nordsick model, whether or not it is any of the successor models there, the general ratio of the silicate to carbon is basically set by cosmic abundance. And so most of those carbonaceous materials have to be in the solid in order to provide the extinction that you need to explain the extinction curve in all the various directions. It varies, of course, with direction, but not by much. You're not talking factors of 2, you're talking 10% or a few percent variation. So the carbon and the silicate are intimately mixed. And that's really the key. When you take the carbonaceous material on top of the surface of a silicate material, that interface is where the reaction takes place, and the carbon reduces the metal oxides that are there and ends up as CO, where the metal ends up reduced to, instead of, for instance, SiO2, to silicate metal. But there's plenty of water, for instance, and other oxygen-containing molecules, but mostly water, in the inner nebula to reoxidize the metals, again, to remake the silicates that are there. That's why you basically don't see a reduction in the CAIs or the chondrules. They're fully oxidized minerals. Although you do see, for instance, a lot of Fe+2 rather than Fe+3 in that case. And again, it's because the nebula was a relatively reducing environment, even though it can contain a lot of oxygen and in water and OH and some other molecules.
Yeah, okay, I see. Thank you very much.
There's also a question in the chat.
Okay.
Have you tried carbonaceous materials as catalysts?
I was challenged when I gave this presentation, or sorry, a similar presentation on this kind of reaction before. I was asked by Larry Nittler whether or not carbonaceous materials did act as a catalyst. And that's one of the reasons why we did graphite. We put graphite in that same reactor that we were talking about before. And then when we took the materials out, again, the same thing happened. The graphite was a perfectly good catalyst. After 10 or 20 runs, it would make the same kinds of hydrocarbons we saw. And what we saw was the formation of these nanotubes. In fact, that was the first time we actually noticed the nanotubes and went back to the silicate materials that we had used as catalyst and looked at the surfaces, and again found the nanotubes, the same kind of morphology nanotubes on the surface of the silicates. They were more obvious on the carbonaceous grains because they grew much faster. I think they incorporated not only the gas phase material from the surface, but we had migration from the silicate, from the graphite catalyst that these things were sitting on. Graphite's more over here. So yes, carbonaceous materials are also acting as catalysts. Was there another question in the chat? I put my glasses on to read that. Yep, no. So the only carbonaceous material we tried was actually just the graphite. The reason for that is that if we put another carbonaceous material in there, I'm not positive that we could tell the difference between what we were starting with and what was coming off the carbonaceous solid. So for instance, a wax or something like that would melt together and do other things that are uncontrollable. The graphite, we could have a particular particle size and do consistent experiments. So that was the only one that we used. Any other questions?
I have one more question. So for me, my reactions hand raise is not working.
Nope, that's fine. My screen has been doing bad things for a while, so.
So in one of the plots, you showed that the CO goes down and CO2 goes up with time.
Yes.
But so I was just wondering, like, why is that? Because, for example, in disks, we tend to see more of CO in like spectra than CO2.
I think because there's more oxygen in this system than there is in the water here obviously is going up with time as well, which is also reacting with the some with the CO, and so we're getting this increase in CO2. If we were in the nebula at much lower pressures, that would not happen.
Okay. Okay. Yeah. Thank you.
Mm-hmm.